Good morning. In the last class, what did we discuss? We have discussed about gradually varied flow, isn't it? Gradually varied flow and water surface profiles, isn't it? So, okay, so my screen is visible to you. Is this visible? Okay, wait. Now, is this visible? Who left the meeting? Now my screen is visible? Visible or not? No. Wait. Now, I think it is visible to you now. Visible? Okay, so last class we have discussed about gradually varied flow, isn't it? So today let's start rapidly varied flow, which is also called, in short form, it is called as RVF. Okay. So this is the rapidly varied flow. So what is the definition? Rapidly varied flow is a significant change in water depth over a short distance. So what is the definition? Definition of rapidly varied flow. RVF is a significant change in water depth over a short distance. Okay. It occurs when there is a local disturbance in the balance between gravity and the friction. For example, the wheel, venturimeter, sluice gate, free overfall, sudden change in slope, okay, or a mismatch. So, when the flow changes from subcritical to supercritical, then rapidly varied flow occurs. Okay. The assumption that the flow varies rapidly over a relatively short distance Relatively short distance means that bed friction is unimportant. Thus, a smooth transition, the total head is usually assumed constant through the short region. For an abrupt transition, there may be significant head loss, but it is associated with high levels of disturbance, not bed friction. So generally RBF occurs and that is called a hydraulic jump. Okay. So suppose this V1 is the velocity at a section A1 and V2 is the velocity at a section A2. Then if flow depth changes from a lower gradient to higher gradient, then there is an abrupt, if there is an abrupt rise in water, then this type of flow is called hydraulic jump. Okay, this is the hydraulic jump. So a hydraulic jump is an abrupt change from a shallow high speed flow to a deep low speed over a lower energy. It occurs when a depth difference is imposed by upstream and downstream condition. And across the hydraulic jump, mass is conserved, momentum is satisfied, and mechanical energy is lost. Okay? Assuming that velocity is uniform over upstream and downstream of the cross section, small slope so that the downslip component of the weight may be neglected. The length of the jump is short, wide or rectangular cross section, and there is a momentum equation for hydraulic jump. This is the momentum equation of hydraulic jump. H2 equal to H1 divided by 2 into minus 1 plus root over 1 plus 8 fr square, Froude number square. Okay. So this is a quadratic equation for the depth H2 divided by H1 and its positive root gives the downstream depth in terms of upstream quantities. Okay, let me show some another notes.
And so, what we've been talking about for the last this week, this section, don't really know where it comes from actually. Let's just do this. I think what we need to talk about in terms of gravity varying flows, the panel doesn't get narrower than cubic.
So, after completion,
So everyone, please, I am sharing one video. Everyone, please listen it carefully. Is this visible? Okay, so let's start.
of this topic, you are able to understand what the concept of rapid flow. You can derive the equation for conjugate depths, or we can say sequent depths, and also you can solve the problems on conjugate or sequent depths. First of all, the depths, or we can say after completion of this topic, you are able to understand what is the concept of rapidly varying flow. You can derive the equation for conjugate depths, or we can say sequent depths, and also you can solve the problems on conjugate or sequent depths. First of all, we'll just see what is a rapidly varied flow. Last time we have seen the gradually varied flow, where the parameters are changing very gradually. Now here, it is changing abruptly, or you can say rapidly. The rapidly varied flow phenomenon is a very unstable, and it has an inherent tendency to change itself to the stable truncal flow, resulting in the abrupt rise in the elevation of liquid surface. The local phenomenon, where the elevation of water surface is suddenly rises, is called as a hydraulic jump or a standing flow. Let us see this figure. The flow is coming like this. Here it is a barrier, and it is coming abruptly down, and it flashes again coming up. See here, this water surface which is coming down, this pollution, and it rises up. The rapidly varied flow we can observe over here. The rapidly varied flow we are observing over here. Here gradually, it is changing very slowly, very slowly, very slowly. Here we can say it is a uniform flow, and this is a non-uniform flow up to where it is going to become a stable one. Now, as the example is hydraulic jump of the rapidly varied flow, we'll see what is a hydraulic jump. When a supercritical flow, where the Froude's number is greater than 1, changes suddenly to the subcritical flow, where the Froude's number is less than a hydraulic jump, less than 1 in the hydraulic jump. Why Froude's number we are taking? Because Froude's number is the ratio of inertia force to the gravity force. Due to the formation of hydraulic jump, large scale eddies are formed and the turbulence occurs, resulting in appreciable loss of kinetic energy takes place. Bedon, it is the name of the scientist, a French engineer, was the first to investigate the phenomenon of hydraulic jump experimentally in the year 1880. 1818. This is the same figure where you can observe sudden rise over here. This sudden rise you can observe here. This section 1 and section 2. And particularly here we are going to adopt, instead of energy equation we are taking a momentum equation. Keep in your mind. Now define a hydraulic jump. The answer is when a supercritical flow changes to subcritical flow, a considerable amount of energy loss takes place. This phenomenon is termed as a hydraulic jump. Now, as appreciable loss of energy changes occurs in a very short length, this is a bit of the channel, it is advisable to apply a momentum equation instead of energy equation along the continuity equation for the analysis of hydraulic jump. As per Newton's second law of motion, algebraic sum of all the external forces in any direction is equal to change in momentum flux in the same direction. Therefore, applying the equation in the direction of flow to the control volume, this section between 1 and 2 is called as a control volume. we will get summation of Fx, that is summation of all the forces is equal to mass of the flow into change in the velocity. So it is rho, mass density, into discharge into velocity, that is final minus initial velocity. From figure, rho, q, v1, v2 are the density, discharge and initial velocity and final velocity respectively. Now the summation of Fx is F1 minus F2 plus W sin theta minus F4 minus F5. See here, F1, it is in the direction of flow, F2, position, F4 and F5. This is a bottom resistance, this is the air resistance. W sin theta is with respect to this flow. Where F1 and F2 are the pressure forces at section 1 and 2, that is from the figure. W sin theta is a component of the body force in the direction of the motion, and F4 and F5 are the channel bottom resistance and air resistance. Generally, F4 and F5 are very small, were neglected, and the channel bottom being practically horizontal, the term W sin theta is also neglected. So, solving these, we will get F1 minus F2 is equal to rho Q2 V2 minus rho Q1 V1. We can solve it step by step. You will get F1 plus M1 is equal to F2 plus M2, where M1, that is a mass at section 1, that is rho Q1 V1, M2 is rho Q2 V2. Dividing the equation throughout by gamma, that is, or we can say, in many of the cases we are taking as W, or you can say gamma, that is specific weight. If you can divide this, you will get, again, simplify it slowly, dividing, you will get this equation, F1 plus M1 by gamma 1 is equal to F1 plus M2 upon gamma. That is, specific force before hydraulic jump is equal to specific force after the hydraulic jump is known as momentum equation for an open channel flow. This particular equation is very basic equation or important equation to derive the equation for the hydraulic jump. Fs, that is a specific force, depends on the depth of the flow, cross section of the channel and discharge passing through the channel. The above equation can also be written as A1 Y1 bar, that is Y1 bar plus Q square upon GA1 is equal to A2 Y2 bar plus Q square upon GA2. This is a very important equation. This equation is called the momentum equation for an open channel flow. Now we'll see what is a hydraulic jump in a rectangular channel. What is the equation for this? For a frictionless rectangular horizontal channel, the momentum equation is the same. A1 Y1 bar plus Q square upon GA1 is equal to A2 Y2 bar plus Q square upon GA2. This we can write as B is the width and Y is the depth. Simplify it to B into Y1, that is the area of 1, and remaining as it is. A2 is B into Y2. Put these values over here. And upon Y2 is equal to 1/2 into bracket depths, known as the ratio of these two. This is also, while deriving this, we should also focus on this, what the quadratic equation.
কি ফালতু কি দেখো
My name is Mohammad Saud Abdul. I am a faculty student in NIT.
So I will continue in the next class. Okay. So let me take the attendance. 30 participant. So I have recorded your attendance. I will upload it later. Okay. Thank you.